coordinates change, right? In Cartesian, there was this coordinate system sitting off to the side, and it was sitting fixed, and it never changed. In this case, we now have one that changed. We have, the way we defined our coordinates, we have one that's tangent to the path, and then one that's perpendicular to that, pointed back at the instantaneous center of curvature, right? So we have an ET is in the tangential, EN is normal, and it's pointed back. And these change, right? So in this position right here, ET would be like this, and EN would be that. Later on, right, the curvature is curving the other direction, EN's pointed back to the middle, and ET is pointed like that. So it's changing. It's like this. It's going, beep, beep, and it's moving around as we go along, okay? And there's reasons why we do that. We defined what ET, EN, S is the distance along the path. We talked about the rho is the radius of curvature, and that's where we left it off. So what we're going to do is we kind of first define the coordinate system, we talk about position, and then we're going to talk about velocity, then acceleration, and then we're going to do some problems. Okay, so here's the velocity right here. Right, so if we start out with velocity, we want to define velocity in this coordinate system, right? Velocity is always tangent to the path. Is tangent to path, right? So velocity is always in the ET direction. In this coordinate system, right, ET is tangent to the path, and so in this coordinate system, the velocity is always in the ET direction. So it's just going to be, how is my position along the path, which is S, how is my position along the path changing with the time, and it's in the ET direction. And what does it mean that it's in the ET direction? It just means that, so you write it like this, you put ET after it, right, ET hat. Just saying it's in the ET. What does that mean? It just means that it's tangent to the path. You'd have to know what the path is, right? It just says that it's always just right along this. And that ET is changing. It's always changing, right? Depending on where it's at. And then we're just gonna be comfortable with it, but we're just gonna write it as being, just like we wrote in the I direction, it was ds dt in the I plus d in the j and then the k. You do the same thing here. You just say it's in the ET direction. Okay, we'll do some examples. You can see it play out a little bit how it works out. Okay, so now we've defined velocity. So now let's define acceleration. Acceleration is the derivative of the velocity. So that's just going to be dv dt, right? And dv we just said, or v we just said was ds dt. So it's going to be v in the ET direction. Derivative of the velocity in the ET direction, always in that direction with respect to time. We have to apply the product rule, so we take the derivative of the first thing, dv dt in the ET direction, plus v, and we'll take the derivative of the second thing and leave the first thing alone. Just like we did for our Cartesian coordinates, right? Take the derivative of the first thing, leave the second thing alone, take the derivative of the second thing, leave the first thing alone. Okay, so that's what we just did right there. In Cartesian coordinates, when we took the derivative of the coordinate system, it went to 0. Okay? In this case, though, it's not going to go to 0, right? Because it's changing, right? This does change. ET does change, okay? And this is where the stuff we talked about the page before, right? I'm just going to write it down here, and then I'll go back and show you what it is. So the ET hat dt is equal to d theta dt in the en direction. So this is omega in the en direction. And say previous page. Right. I told you this was coming. I said, like, if the base vector's changing, so I'm saying is if we go back up here, just the page before, we had this little discussion. There's a whole section in the book about this, right? And it's just saying, hey, if I have a base vector that's changing, which it's rotating with an omega, we could say that how it's changing right here is going to be d theta dt in the n direction. And then, so it's normal, d theta dt in the normal direction. And in our coordinate system we just had, normal direction is going to be the en direction, right? Do you really have to completely understand what happened there? Not really. Just know that just trust me that it works. You could do that. Okay. The base vector change, it becomes that. All right. So we're gonna take that and then substitute that in up above. Right. Which then becomes this. Right. So this is one more comment here. dv dt is just v dot. Right. How velocity is changing with respect to time. Remember, the dot just signifies the derivative with respect to time. Right? And so if we do that, this is what we get. So this is what acceleration is defined as. See, it gets a little bit more complicated than Cartesian coordinates. Right. So that's how we define acceleration. Right? It's how my velocity changes in the ET direction, and then this other term on the side, right? V times theta in the EN direction. Right? We're going to write it in a little bit different form that you'll recognize it in a second, but this is change in speed. It's acceleration associated with change in speed. Right? And this term is a change in direction. So we kind of separated it out into two different components. We have a acceleration associated with changing in speed, right? So if I was accelerating, like in a car, if I'm riding in a car and I step on the gas, I'm going to accelerate, right? I'm going to go faster, and that is captured by this, right? I'm stepping on the gas and getting the torque out of the car and getting the acceleration. That's V in the ET direction. The other term is associated with I change direction. It's what you would feel if you turn a corner, right? So if I go up, I'm accelerating, and I go, or say maybe I'm even just going to constant velocity, and I take a corner and I turn to the left, right? I have to accelerate back towards the middle. If I don't accelerate back towards the middle, then I'll keep going on the same path. And so we separate. What do we call that when the acceleration would change the direction? Oh, come on. You've heard this word many, many times. No, Nate Dogg? Logan? Mark? What? Which one? Oh, is there two Marks? Oh, Mark, right? What we got here? What's that called? We know what that is. The acceleration change with the direction. What is it? What comes to mind? There's no wrong answer. I mean, there are. I won't shame you, though. I won't shame you. What? No. So, I mean, I don't shame you, and then I no, you dumbass. It's not that. Why are you guys scared to answer, huh? But no, torque would be it would be causing it alpha. Torque will cause an alpha, which we briefly talked about before. Omega would be changing with that. Oh, what? Centripetal. Right? Everybody's heard the centripetal. Centripetal acceleration, right? So that's the centripetal. It's in a form we haven't seen before, right? This V, that's exactly what it is. It's a acceleration associated with that, and it's real. There's you're like, oh, is there really I mean, at least when I was your age, it was like, oh, okay, well, we got velocity, and if I change my velocity, that's clearly my acceleration. Like, is there really an acceleration associated with change in direction, or are we just kind of making stuff up? Absolutely, there is. And how you know that it's there is that you'll feel a force that's going that direction, or you have to apply a force in order to go that direction. And if there's a force, then there's an acceleration, right? And so an example would be, right, if you take a mass on a string and you start whipping it around, right? There gets tension in that cord. There's some force that's pulling that thing back to the middle, right? And that force that is associated with the change in direction, right? That it wants to keep going that way, and then the string is like, nope, you have to accelerate back this way. And that's an actual force that's there, and because there's a force there's going to be an acceleration. Or if there's an acceleration, there has to be a force, right? Or in your car, when you take that corner, right, your body wants to keep going straight, but then the car is saying you got to turn left, and so there's a force that pushes, the door pushes back on you, saying you must come with me this direction, right? Or the tires and the friction on the surface, the tires are the friction on the surface is applying a force to those tires to make the car turn in that direction. So there's forces associated, so there's accelerations. And so that's in its purest form, that's what it is right there. So let's look at different forms of that. Right? Other forms of theta dot, okay? So we're gonna go back to this little curve over here, right? And we've got a d theta down here, and I've got a rho right here, and I got a ds right there. Okay. And so you can calculate arc lengths. ds is equal to rho times d theta. Right? So if you're talking really small things, you can figure out how long an arc length is by just taking that radius, multiplying it by the theta, and it'll tell you what ds is. And that's how, that's where you get the circumference of a circle, by the way. You take 2 pi is the radius going all the way around, and then you is the circumference all around. 2 pi is the angle all the way around, right? And then the radius is obviously this radius. If I want the whole, I take that radius and I multiply it by 2 pi, and I get the circumference. So that's what you're doing. So you can actually do that at a smaller state, right? In differential form, we just say rho times d theta is equal to ds, that arc length right there, right? And we come back up to what velocity, that velocity term, velocity is equal to ds dt, and we could call that ds, we just said it could be written as rho times d theta dt. So this could be rho times theta dot equal to rho times omega. And so there's just kind of using that to kind of write this thing in a couple different ways. Velocity can be rho times theta dot, or it can be rho times omega, right? And so this basically comes from that. I just kind of rearranged the stuff from above. So omega could be written as theta dot, or it could be written as the velocity divided by rho. Okay, and so let's look at the different forms here. So if I'm talking velocity in this coordinate system, just kind of brief little summary of what we just talked about. We have velocity is v times et, in the et direction rather. So that's just going to be ds dt in the et direction. So that's the easy one. Velocity is really easy in normal tangent. It's just my ds dt in the et direction. That's all you state. It's just in the et direction. My acceleration, though, is going to be at in the et direction plus an in the en direction. So we have the acceleration associated with change in speed and acceleration associated with change in position, right? At is just going to be v dot. So at in the equation right above here, right? That's just going to be v dot. Or an can be written any one of these forms down here, right? This is how we derived it. We derived it with this, v times theta dot, but if I take this stuff and I substitute it down, I could also write it as v times omega, or more useful would be v squared over rho, right? Or rho omega squared. Right? Either one of those work. So depending on the type of problem you're doing, one of these may be more interesting or may be more useful than the other, right? If you're doing something where you know what omega is, when you're talking about an right here, you'll use rho omega squared. If for some reason you're doing a problem where you know velocity, then you'll use v squared over rho. And these ones are what you should recognize more. When we talk centripetal acceleration, usually we talk about r omega squared or v squared over r. So then maybe if I would have said that originally, you maybe would recognize that as centripetal acceleration, but that's what that is, right? And to highlight, right? Remember I just gave you a big speech about how those forces are really there. And if they're not there, right? If the force isn't there, then you take off at a tangent, right? So if I had a ball on a string and I'm whipping it around, if that tension force goes away, then boom, you take off on a tangent, because now I'm not applying a force to tell the ball it has to accelerate back to the middle. If there's no force there, there's no acceleration, so it takes off on a tangent, okay? And so this is my YouTube Monday we're gonna look at.